we're just testing the mic, but we can start anyway.
Yeah.
So welcome to IETF Friday morning MAPRG session. I'm Mia Kulevit.
And I'm Dave Planka. I thought Miriam knew that.
But other people might not know. Yeah, so this is an IETF session. We also have basically a note wall, which is kind of aligned with the IETF note wall, but slightly different terms. But I guess you've seen that. What this note wall is actually not pointing at is the code of conduct and harassment policy, but it's also important things to note. So please be aware of all these things. This is the usual slide, which is in there for your convenience with our mailing list and also the Jabber room and the link to this session. May need to look it up later. And this is our today's agenda.
Take this. Just a couple things I wanted to mention about the status of the group. Things that are really healthy in MAPRG. As well, you know, we have a lot of people. We always have a packed agenda, as we do today, and we'll work our way through here. One of the things I wanted to mention is the last couple meetings I went to PRG, the Privacy Enhancement and Assessment Research Group. That's measurement related as well, and they're doing some interesting things. So look for opportunities, I think, to sync up with what they're doing and watch what they're doing, especially when it's about privacy with measurements. The next thing, let's go to the next slide. Here, yeah. So this is the way I was greeted when I got my badge this week, non-Planka, and maybe they're anticipating that I won't be there at the next meeting in Singapore. So so we have one Planka this time and non-Planka next time. Can you go to the next slide? So Miri and I are going to call for an alternate or additional MAPRG chair. We've been running this for about 4 years. I'm not meaning to step down from it, but we could certainly use help with another person when we're covering meetings in different parts of the globe. So if you're planning to attend IETF 106 in Singapore and are interested to work with the two of us on preparing the agenda and vetting and reviewing the candidate work there, let us know. We're especially looking for someone who is in academia, not because it's a credential that you need, just because we're both in industry right now and you might have some contacts that we don't have or aren't as up on. So it's not a requirement, but if you have that, you might like to join. And then, like I said, you'd be able to curate the upcoming program, which is kind of fun, and it's a little bit of work about, like Miria this time, for instance, did a lot of legwork or contacting people to get the program filled out. So feel free to write us about that. I think, is that the last thing we have there? Yeah, that's the last of that. So our first presentation is going to be remote because Yoder Song is in New Zealand and it's very late there. So we're going to let them go first. And let's see, Yoder, are you in the? Yeah, I see it in the Jabber. I mean, sorry, in the Meet Echo.
Hello.
Hello.
Hi. Can you hear me all right?
We can hear you fine. You're ready to go. We can see
yeah.
the slides.
Yeah. So, hi everybody. My name is Yoda Song. I will be presenting the paper "Understanding Evolution and Adoption of Top-Level Domains in DNSSEC." This paper was recently published in the 2019 IEEE MNN Measurements and Networking Conference, and the other co-authors of this paper are Surya Ravichandran and Dr. Aniket Mahanti, both also from the University of Auckland. Next slide, please. So we focused on the top-level domain and second-level domain in the DNS hierarchy, and we also provide a brief overview of DNSSEC implementation in New Zealand specifically. A generic top-level domain, or GTLD, is one that does not represent a country, for example, .com or .net. And a key motivation for this study was the new GTLD program introduced by ICANN, which introduced over 1,000 TLDs to the internet since 2013. Next slide, please. So this is a timeline of the generic top-level domains and when they were introduced. So in this presentation, we will classify generic top-level domains into 3 groups: old for the ones created in the 1980s, early for those created between 2001 and 2012, and then new generic top-level domains for the thousands of new generic top-level domains introduced since then. We will also look at country code top-level domains, or CCTLDs, later on. Next slide. So in terms of the related work, this paper extends upon the 2015 paper in analyzing top-level domain and second-level domain adoption. We also later on briefly look at DNS6 implementations, specifically in the context of the New Zealand top-level domain .nz. Next slide. For data collection, we used two different sources for our data. So we collected packet traces from the campus network of the University of Auckland, which is the largest university in New Zealand with over 40,000 users. In addition, we also collected metadata from Internet NZ, the manager of the .nz New Zealand national top-level domain, for 3 national-level datasets. We then classified the generic top-level domains into the 3 categories: old, early, and new, based on the time of introduction. And finally, we carried out the top-level domain and DNS6 analysis in the end. Next slide. So moving on to results. Next slide. For a trace overview, we found the number of DNS queries to grow between 2013 and 2018, with the proportion of requests to early GTLDs, new GTLDs, and country code top-level domains all increasing. While there has been a lot of growth in the new generic top-level domains compared to 2013, they still only account for around 0.3% of total requests in the local campus network. Next slide. In terms of the top 10 most queried top-level domains, we find some common old generic top-level domains like .com, .net, .org. And in terms of the country code top-level domains, the .nz, .au, and .cn for New Zealand, Australia, and China all regularly appeared in the top 10 every year. There were no new generic top-level domains at all in the top 10 in any of the years. And for the early generic top-level domains, the only one to appear was .info in 2014 and 2018. Next slide. So for unusual top-level domain usage, we notice the country code top-level domain for Slovakia, or .sk, to rank 4th in both 2017 and 2018. We found over 99% of these DNS requests to actually be machine-generated as part of the antivirus software used by the university. So different from the fully qualified domain names of usual websites, such as, say, www.google.com, we find the fully qualified domain names of these machine-generated requests to be much longer and containing seemingly random combination of alphanumeric digits. So while there was rapid growth in the number of queries to the Slovakian.sk TLD, we find that this growth was not actually driven by human activity, but rather just the machine-generated DNS requests. Next slide. And we also found, in terms of unusual TLD usages, that the country code top-level domains, which were not restricted to only the citizens of that region, may be often used as generic top-level domains instead. For example, the .io country code top-level domain for the British Indian Ocean Territory was top 10 most queried in both 2017 and 2018. And this was not due to interest in the region itself, but rather because the top-level domain is quite popular among startups and open source projects online. So .io and several other similar country code top-level domains that are now heavily used as generic top-level domains instead are now classified by Google as GCC TLD, or generic country code top-level domains. Similarly, we also found that the usage can be used by domain hack or concatenating sections of the fully qualified domain name to form a different name. So for example, this is commonly seen in the YouTube link shortener youtube.be, which uses the .be country code top-level domain for Belgium. So what may now be a country code top-level domain may be more accurately described as a generic top-level domain in the future. So the top-level domain classifications we identified earlier will need to be regularly updated to reflect the changes. Next slide. In terms of TOD growth from 2013 to 2018, we find the number of queries to new generic top-level domains to far outpace the old generic top-level domains. And there was also some spillover effect into the country code top-level domains, where the generic country code top-level domains, as classified by Google, grew at a much faster rate than non-generic country code top-level domains. Next slide. For these rank frequency plots, the top one is for 2013 and the bottom is for 2018. So between these, we can most notably see the growth in the number of new generic top-level domains. We can also observe that there was a zip slow in the old and early generic top-level domains, and that the new generic top-level domains are much less concentrated, as shown in the flatter slope in the graphs. Next slide. In addition to the top-level domains, we also looked at second-level domains. So in this example here, the .co for company before the .nz New Zealand country code top-level domain is the second-level domain. So similar to the new GTOD program by ICANN, the second-level domains in New Zealand were open to public registration in 2014. So this means that instead of choosing from one of 15 predefined second-level domains, a company can theoretically use any name as the second-level domain. So these second-level domains account for over 20% of all new domains, but only account for 0.6% of the total requests in the local network. Next slide. One of the potential problems from opening both generic top-level domain and second-level domain registration to the public is that there could potentially be overlaps between the two. For example, Kiwi is a term used to describe New Zealanders, and currently there is both a .kiwi top-level domain as well as a .kiwi.nz second-level domain under the New Zealand.nz top-level domain. We found an unusually high number of .kiwi.nz domains registered shortly right after their release, as shown in the spike in the graph, which we think could be due to cyber squatting from those who already have .kiwi domains and wanted to avoid others registering for similar domains to their own. Next slide. So for DNSSEC overview, we found a spike in the DNSSEC implementation in 2016, likely from Cloudflare's introduction of universal DNSSEC. We also found that since then, the insecure delegations are slowly growing again, and that while the proportion of signed domains with expired signatures has decreased quite significantly since, the invalid DS records still remain high with little improvement over the last few years. Next slide. So for the takeaways, next slide. The takeaways for the domain names. So we find newly introduced generic top-level domains and .nz second-level domains to grow in popularity, but still not very heavily used yet. An advantage of new generic top-level domains is that because there is less popularity concentrated in the most popular domains, cyber squatting on a large scale is theoretically less feasible compared to cyber squatting on the older generic top-level domains. However, a potential problem we found is the overlap between similar domain names at the top-level domain and second-level domain level, which will require further coordination in the application stage to prevent this from happening. Next slide. So for DNSSEC, we found the implementation in New Zealand is growing, but the chain of trust is incomplete. The main problem being that the incorrect DS records, without which it is not possible to authenticate the public DS key records in the child zone. We found an improvement in the reduction of expired signatures as a proportion of the total signed domains, which we see as a growth for the DNSSEC implementation in New Zealand. Next slide. So finally, the concluding remarks. So in this paper, we presented a longitudinal analysis on the adoption of new generic top-level domains and the deployment of DNSSEC in New Zealand. New generic top-level domains are growing in popularity, but still not very popular yet. And we believe there needs to be more work done on exploring the top-level domain topic further before the second round of new generic top-level domain applications in the future. Thank you.
Thanks, Yoder-song. So we've got time for Q&A, and I see George is up at the mic over here, so let's go there.
Hello, George
Hi.
Michelson from APNIC. You can hear us?
Yes.
So I think a study like this needs to explore the concept of DGA, or generative domain names, hash names, which are a mechanism for command and control in botnets. And so aspects of behavior in the new GTLDs relate strongly to compliance checks on how you justify your need for a name. The old GTLDs and CCTLDs tend to be harder places to get a name, and the newer, younger TLDs often are attractive targets for bad actors. You talked about ESET using hash names and machine-generated names for good purpose, but I think you have to address the question of the use of hash names for bad purpose. The second thing is that many of the new TLDs have no intention of offering delegation services to wider public industry. .ibm is not an open domain. It is a private, closed domain, and its growth will be a function of IBM's mission. It's not a function of a market process. It's a function of their need for labels under IBM. The third and last comment is that you typify CCTLDs as if there was some normative behavior that is prescribed by ICANN. But the quality of a CCTLD is that it reflects an independent economic or nation state that in effect is a UN chartered entity that has standing as government. It's not about a contract binding or a belief of meaning. It's about the fact that they have an army. And so they are only different in the quality that they own tanks, and not specifically that any legalisms govern what they do. But your paper was very interesting, and thank you for presenting it.
Thank you. Thank you very much.
Tim Rottenberg. So,
Can I actually quickly ask you to step over to the other mic, because that's where the video is currently.
okay. Hi, now I'm on video. So thanks for your talk. What I would be interested in, and maybe you can a little bit elaborate on that, is where did you get the data, or which kind of data did you have for your analysis? So you talked about that you had a collaboration with the top-level domain registry, but what did they give you, and which kind of measurements or analysis did you do on that data?
So there were 3 data sets we collected from Internet NZ. So they were in the presentation. There was specifically the DNSSEC overview graph, as well as the second-level domains created over time for the .kiwi.nz slide.
Okay, and you got like these numbers from them, or did you had like, I suppose you didn't get any zone files or something like this where you did measurements on?
Oh no, it's just the numbers, not the detailed zone files. Yeah.
Okay, and as a last remark, I just wanted to drop the RIPE Atlas project. If you want to do DNS like measurement stuff, you can also do like any kind of DNS records there, also limited to geographical regions or something like this. That might be interesting for future research. Thanks.
Thank you.
Hello, this is Ulrich Wisser from the Swedish Internet Registry. First, I want to say to George, we are not a government agency. We never have been. We never will be. The Swedish government has not been involved in the running of the .se registry. And for the record, we don't own tanks. So CCTLDs are really very broad over the map. So, but back to the topic. You said that there is a lot of domains, more domains signing DNSSEC than there is domains sending in DS records. And in that, I would like to know, do these newly signed domains support the CDS/CDNS key? Because that is then something that registries could actually use to foster the adoption of DNSSEC.
From the metadata we were available to collect, I don't think this information was available for us to see, so I can't comment on that.
Thank you.
Thank you.
Ben Schwartz, Google. You mentioned that 10% of DS records you saw were invalid. Could you clarify what you mean by invalid here? So, for example, are you saying that those domains, if I tried to resolve them through a validating recursive, would fail with serve fail?
I believe it's the DS record don't match with the hash of the child the DNS key records, but I'm not entirely sure on that.
Okay, thank you.
Thank you.
Kazunori Fujiwara from JPRS. About top 10 most queried TLDs.
Could you speak up to the mic a little closer? Thanks.
Kazunori Fujiwara from JPRS. About page 8, top 10 most queried TLD graph. I did a similar analysis by using root server's data. And which data do you use?
The top 10 most queried TLDs was based on the local campus network.
Local?
The campus network. We collected outside.
Okay, I see. Thank you.
And if I could ask one last quick question, Yoder-song. You mentioned in your takeaways the problem of the overlap, for instance, the .kiwi to .kiwi.nz. I was just curious, how effective can one be at identifying that those are essentially clones, or what are the methods that you use or you can imagine we can use to determine that they're essentially aliases? Do you have to do active measurements, or can you determine it passively from the registrations?
We actually didn't look specifically into the domains that appeared in .kiwi and .kiwi.nz, but I think that we can look into that further in the future.
All right. Well, have a good evening. Thanks for staying up late and presenting this work to us. And let's a round of applause for our speakers. So Tommy, we're ready for you. So Tommy's coming back to update us, I think, for the third time maybe on some measurements.
Yeah, so this is, hi, I'm Tommy Pauly, and I'm going to be sharing some client measurements that we've taken. I'm at Apple, and so this is information that we get from looking at sampling from iOS and macOS devices. Previously, we've shared a lot of information about how we see IPv6 adoption, and I'm going to be sharing a little bit about that now, but one of the new cool things that's happening is that we see a new protocol version, TLS 1.3, coming out and ramping up. And I wanted to share some information about how we see this happening. So as some background on what we're looking at here, TLS 1.3 was published as RFC 8446 last August. It had been in development for a while, but things were not really deploying it at large scale yet. Now on our clients, we enabled TLS 1.3 by default for pretty much all connections in March. And so this was iOS 12.2 and macOS 10.14.4. So at this point, we were able to start collecting data about how often we see TLS 1.3 actually being negotiated with servers that our client devices are talking to. And anecdotally, we had heard, and I think many people are aware of TLS 1.3 being rolled out. We were aware that many server deployments were turning it on in some percentage and increasing it and ramping up support. But at least I have not seen a lot of data shared from either server side or client side of exactly what scale we are seeing yet. I would love to see data that anyone else is willing to share, but we thought we would kind of take a step here and let people see how the adoption is going. So the questions that we asked before looking at the data was, first, how much server adoption are we seeing of TLS 1.3 from the perspective of the clients? Like, how much is this growing? And then also, one of the key things about TLS 1.3 from a measurement perspective is that it's supposed to have some performance benefits. In almost all cases, it can shave off one round trip from handshake time. So we want to see, is this actually playing out in reality? How is this actually improving the overall connection establishment time that we see from the client? So before I get into the data, just some notes on the methodology. We are collecting this data on a per connection basis. And in this case, it's a per TLS connection. We're not looking at, for this data, anything that's not a connection that has TLS enabled on it. And this is all going over TCP. What we're collecting is the TLS version, how long the TLS handshake took, the ALPN value that we negotiated over TLS, is this HTTP1 or HTTP2, as well as information about the address families. Are we going over v4 or v6? And are v4 or v6 enabled on the network that we're connecting over? And so because of all of this, what we're representing in general is the amount of TLS 1.3 that is being used. This is not strictly the number of servers or the percentage of servers that have enabled 1.3, but rather like the percentage of popular servers, or how often are clients really using this in practice. We imagine, of course, that there is a long tail of things that have not turned on new protocols, but that users don't often access. And the data for this presentation is being collected over around a 3-month period. This represents April to June, and it's a random sample of, for those devices and those users who have opted into data collection, 0.05% of all of the connections. So there's a large scale of connections, and this is getting a lot of data, but it's a small sample of it. All right, so here we see a trend over the 3 months we are sampling. The green is the amount of TLS 1.3 that we see compared to the overall amount of TLS. And I'm only showing TLS 1.2 and TLS 1.3. The older versions are there, but they are extremely tiny. They are less than 0.5%. It's not interesting. And so we see a really steady march up, 10%, 17%, 22%. The amount of servers that are turning this on is definitely growing. But we had other data in here, and so we wanted to start correlating it. And it's very interesting if you look at this same trend when we look only at connections that established over IPv6. And here, it's a similar trend, very similar line. So we see the numbers are kind of being ramped up on these servers. But the absolute numbers and the absolute values of TLS 1.3 are much higher. And as of June, we are already up to 1/3 of all of our connections. When we were going over v6, we're using TLS 1.3. So this is great. So looking a little bit more into this kind of correlation, because this was an interesting thing we noticed in the data, so we wanted to dig a bit deeper. We asked the question, how likely is a server to support TLS 1.3 if it is also upgraded to support IPv6? So this data is now only looking at connections that are established when we're on a dual stack network. So we have both v4 and v6 available. We're asking for both A and Quad A queries. And so we're essentially checking, does this server support v6? And we see that of the arguably larger number of v4 only servers, only 12% of them by June had adopted and enabled 1.3. But of the servers that had previously already been rolling out IPv6, that number is over a third, it's at 36%. So there's a fairly strong correlation there. And kind of looking at this the other way around, when we look at the overall amount of server enablement of IPv6, today when we're on dual stack networks, we're seeing about 40% of connections go over IPv6. But when we sample only for those that are going over TLS 1.3, so people who have been upgrading recently, we see that at almost 70%. So if you're looking at new TLS connections, these are almost all happening over IPv6. This is an interesting correlation here in the data. Similarly, we look at the correlations with ALPN. So how likely are you to support TLS 1.3 if you have also upgraded to support HTTP 2? And again, it's actually a really, really similar number. So if you remember for v6 and v4, v4 had, I think, was 12%, and v6 had 36 or 38. And here we see almost exactly the same numbers. If you are kind of a legacy server, if you're doing HTTP 1, there's only 13% of them have upgraded their TLS. But for HTTP 2 connections, over 40% of them are already on TLS 1.3. And again, looking at things the other way, we actually see overall from our clients about a 50-50 split of connections use HTTP 1 or HTTP 2 on any given network. But if you only look at the connections that are using TLS 1.3, we see 75% of connections are using HTTP 2. So again, an interesting correlation and really quite similar numbers here. And then the last thing we wanted to look at was the performance to validate that other question, are we seeing the performance gains that we were expecting with TLS 1.3? And here the answer is pretty clearly yes. So this is a PDF showing the number of milliseconds that we see for both TLS 1.3 and TLS 1.2 handshakes. And we definitely see a much stronger skew towards the faster handshake times with TLS 1.3 than we do with 1.2. So it is clearly a benefit. All right, so that's the data we have to share. So the overall observations we're making is that TLS 1.3 support has more than doubled over the past 3 months. The performance wins that we expected are being clearly demonstrated, and we're getting a lot of value here. And then the other kind of correlation insight is we're noticing trends of these kind of two populations. We're getting bimodal populations of leading edge servers that are doing TLS 1.3, HTTP2, IPv6, and then some straggler populations that are doing TLS 1.2, HTTP1, that are IPv4 only. And so, client developers are looking at needing to optimize for two different populations here, and they should be kind of expecting these general groupings. And it's also, I think, interesting when we're looking at new protocol adoption. I know that these three protocols represent definitely different groups of people at the IETF, and I think it shows that we have a lot of common interesting common patterns, that when we look at the devices that haven't been upgrading to v4, those are kind of common enemies of apathy or inertia that all of these protocols are trying to fight against, and we're kind of all in it together on this. So questions, please.
Hi, George again. Can I just check, is this a sample set mediated from your experiment in the client, or are you doing some traffic measurement at exchange points, or are you bound on the server side? I might have missed it. Mm-hmm. It informs the next question. So this is your mechanism in Apple for measurement of client view of server behavior.
Right. So this is on the population of both beta users and users who have opted in to data collection on across the world on just normal devices that people are using. So generally Wi-Fi cell networks that users are on.
Right. So I'm not using skew in a negative kind of pejorative sense. I'm just observing. If you
Absolutely.
exclusively were in the domain of the Apple handset in mobile, distinct from, say, Apple and Android, you would have some question around, is this a function of update cycle and availability of things? Because this is a client negotiation, right? The server proffers, and then you have a downgrade. So it comes to a question, is it only newer devices you recruit? Is there some skew here that affects the relativities? Because if you were across
Yes.
a random population, V6 would naturally have a higher uptake of 1.3 because it tends to be present in the newer software releases on carriers, and 80% of everything is V6 in mobile. That was really the only point. And it's not to criticize.
Yeah,
I actually
absolutely.
think this is great data, but I just wondered if that was an aspect.
Yeah, that's a really good point. And so I will add to kind of like methodology in the population here. We are only gathering this data from the people on operating systems that have upgraded to enable 1.3. So these are not going to be older devices. These are, of course, not devices that we don't own. So it is an early adopters on the client side.
Just one thing to interject. We've got about 4 minutes and 5 of you in the queue, so let's drain that out. And please remember to state who you are.
Ian Sweat, Google. Thanks for presenting this data. There was a similar question about selection bias. Actually, I was wondering if you had attempted to do a holdback experiment where, say, half the users did not have TLS 1.3 enabled, but recorded when TLS 1.3 was available, and the other half actually used it to get a better idea of because that would remove the server selection bias that might otherwise be present. And we found it for quick. That's kind of important. But that being said, I suspect your data is still largely in the same direction. I just thought I'd ask about that.
Yeah, so earlier on, before we turn it on by default, we were doing probing, essentially detecting when TLS 1.3 was available, even if we didn't use it. Kind of just as a product decision, we decided to turn on full blast for everyone. Because there's the performance win, we didn't want to hold some people back. But yes, that's a very good point.
Jan Rüd. Regarding your last measurements with the PDFs, I was wondering, you basically showed TLS 1.3 servers seem to be better connected, more up to date. What is the reason for the PDF being so low? Is it that they are just better connected, or is it the protocol that is better?
Yeah, that's, again, a very good point. There's lots of biases that get introduced to this data. And I think the other information that we showed of these are clearly servers that are adopting on the leading edge means that they're probably optimizing other things more. I think in at least isolated measurements, we definitely do see the benefit of 1RTT. This particular data is only looking at the handshake establishment time, right? So the RTTs are a major factor in this. So I do think that does dominate this, but you are correct.
Thank you.
Roland Freisich in Element Labs. I really liked your remark about there being sort of the leaders that are deploying new stuff. And I was wondering, could you, if I can put in a request, look at whether or not these people have their domains DNSSEC signed and whether that was validated by just looking at the AD bit in the DNS response that your clients get?
We don't have that, but that'd be great. Yeah.
Could you do that? That'd be great. Thanks.
Well noted.
Hi, Brian Trammell, not as PNRG co-chair despite the hat. With another bias question, which I'll actually phrase as a comment, because I think the answer to the first question we know. There are a few things that you could look at in the responses that might identify server software. So that you could essentially correlate some of these sort of early adopters and stragglers by what the software that they're running. Because one of the things that we saw, for example, with ECN is nobody actually cares about turning it on. It's just that the defaults are better. And one thing that would be really great for this community to know is to what extent is the work that we're doing toward driving the defaults forward driving some of this deployment, and to what extent are these people who are making actual decisions based on the merits of TLS 1.3? Thanks.
Yep, that's a great question. There's, of course, concerns for us about trying to do too much explicit fingerprinting for privacy purposes, but I think developing ways of doing this that are privacy preserving would be a great idea.
Jana Yengar, I was actually going to say something very close to that, which is, have you considered looking into fingerprinting the SSL libraries that are being used at the servers to see if there's a correlation between, if it is possible that maybe there's one SSL library that happens to have bad defaults or bad, and you turn it on and performance actually sucks, which is why people have it turned off. I don't know, but that's one other correlation that I was interested in. But I don't know how easy it is to fingerprint SSL server libraries, or how feasible it is for you to do it, even if it is possible.
Right. And of course, there would be the concern about kind of ossifying on the fingerprint that the given implementation has. We've been seeing actually issues on the other side of certain like firewalls or other measurement devices expecting certain patterns of our own TLS implementation and having changing behavior based on that. So it's a tricky area. Yeah.
So just a very quick question. I did not see any breakages mentioned in any of this.
Yeah, we weren't sharing breakage numbers, but it's essentially very low and pretty much the same as 1.2. We don't see anything that's really specific to TLS 1.3.
That's lovely. Thank you.
Thank you.
Okay. Thanks, Tommy. Gauri's next. We have now two talks related to QUIC, as you expect us to have usually. Sorry.
Hi, I'm Gauri Fairhurst. Yep, I'm going to talk about QUIC. I'm going to talk about some results from a testbed we built. We used Vagrant to configure some computers, virtual machines. We ran tests with QUIC. We used Quickly. Thank you for the people who helped us do that. And we put a real high delay path between our two endpoints. This work was jointly done by me, Anna, and Tom. We're all from Aberdeen University. So this is a summary plot. This is a summary plot of a lot of experiments. And you can see, maybe look at the left box first. And you can see red, which is straight using TCP to do a wget, this time of 100 kilobytes, across this satellite link. And you can see it takes 6 seconds to transfer. There are some outliers. And this is working across the whole access path from the satellite and the internet and doing the measurement across the path. Then if you go to the green box in the left one, the green box shows with TCP using TLS 1.2 to get the same thing. And the green box shows the advantage of a PEP, the performance enhancing proxy, which the satellite operator put in their network. And you can see it's much better on the left with the green than the red. So the real question is now, what does QUIC do? Well, QUIC has to use the full path. It has to go over the satellite can't benefit it. So it does quite well. It does almost as good as the PEP. So which is really good news. Thanks everyone for working with QUIC. However, it's not quite as good as the PEP. And little bits make a big difference when you do web performance. Let's look at a bigger transfer. That's the one on the right. There you see the red plot goes a little bit wild. Why? Because when you're using TCP and you've got a high bandwidth delay product and something goes wrong, the pathology can go many different ways. SS thresh can get clamped low and all sorts of things can happen. So big variance on the right. QUIC did well, but not quite as well as TLS 1.2. Aha, just a minute. We had a previous talk. What about 1.3? Let's put 1.3 in here. QUIC is using 1.3, so it should be as good as TLS 1.3. And now we see the gap, because TLS with 1.3 is much better than TLS with 1.2. Thanks everyone for doing TLS 1.3. That worked really well. And QUIC isn't yet, as we tested it, as good as the TLS 1.3. There we go. That's all right. Let me tell you more about what we're actually using as our link. It's a satellite access link. It's a commercial offering. We're using an engineering platform. The forward link has a bit rate nominally of 10 megabits per second, and you can easily get 8.5 megabits using iPerf across this. Reasonably good service for an ISP. Return link is 1.4 megabits. Pretty good. Not as much asymmetry as many people will have at home if they're using satellite, but I mean, that's okay. Bandwidth delay for the very large majority of packets was just over 550 milliseconds. However, let's look at some long-term measurements of what actually the RTT was. You'll see the blue bar is the average RTT, and it's a high bandwidth delay product link, nearly always at around 550 milliseconds. But there are many outliers. This is because there's a radio link underneath. It's trying to manage the resource. Occasionally you'll get resource requests which can't be satisfied because you've got a lot of contention. Busy times of the day work badly. Occasionally resource requests will fail. You have to try a second time to get resource. Or your pattern of traffic changes abruptly. So these are single packet measurements, and you see these large outliers. So I assert this is a wonderful test case for testing a quick implementation. If you want to push this implementation in a weird way, check all the timers work, check all the transmission stuff work. This is a great environment and it's real. So we're carrying on doing this. We've done a lot of measurements. One of the things we've done is plotted TCP as sequence number divided by MSS, because that's a thing that's roughly equivalent to the quick packet number, and you get plots that look like this. Okay, I mean, there's lots of these, there's lots more in my data set. If you're interested in these, come and talk to me, and maybe next IETF we'll organize a side meeting to go through this sort of data with multiple people. I'm not going to take the question to the end because I'm going to end on a rather different note to where I'm going. This is the download, and yeah, a lot of the time Quick does well, sometimes it didn't do as well. Remember, TCP has this pathology as well, so what we need to do now is look carefully at exactly what's going on the link. Logging is wonderful. We can get a lot of logging out, we can really drill into it, and bursts are not wonderful, so we have to figure out how bursts interact, how timers are interacting. Yeah, okay, so we have lots of data. What do we conclude? I thought I might get some people at the mic, so I'm going to be quick. Quickly was wonderful. It was a great experience using it. Thanks. Right. No complaints about this. We added to the logging available, but then we're already talking about what we should log. TLS 1.3 had a 2 RTT advantage, 1 or 2 RTT advantage, always better, always good. Performance of Quick over satellite was not as good as for TCP with a PEP, but it's within shooting range, so I'd really love to try and get the NIT signed out so it is as good. Downgrading to TCP is not a long-term solution for these people. These people are currently actually pushing you to use their PEP in many cases because it's a predictable environment. That's got to stop. We've got to enable Quick over this network. To do that, we must make Quick work well. To do that, we must understand Quick well. And understanding performance issues falls into 3 parts. Some of this just probably implementation. I mean, we're getting there, but there are things that could be changed. Maybe small changes to the spec in areas of transport. Maybe there's some simple new mechanisms that could really help. Love to explore that. I'll bring that up to the IETF as we find out. We've just started. I'm trying to say how exciting this is. We've just started. We'll continue doing measurements. We're going to talk about logging and tracing because we're currently building our own tools. They're not bad. They're parsing JSON. They're taking PCAPs for the TCP, putting them together. The QLog stuff could be really fun. And if you're a satellite person or a radio person and somehow we can run our tool across that using our virtual testbed, that would be cool to get a wider spectrum of results. My slides have quite a few extra bits, but I don't intend to go through them unless people really want me to. Thank you. Questions?
Thank you, Gori. It's actually a great thing you did that, and it's particularly great to have the traces so people can do a simulation and tune their stacks. The one little caveat I have with your talk is that you are mentioning Quick when in fact you are testing a specific version of a specific implementation. And I bet you, I mean, we had 19 implementation of Quick at the last interop. if we tried all 19 of them, we would get 19 different results.
I think at the moment, I'm not sure I completely agree that when the 19 are finished, they will be that different on that sort of test. If we push harder on better tests, which we will go to, I'm sure we'll get very different results. So, yeah, okay. But my purpose here isn't to...
We do get different results on local tests, on network tests and things like that. So it's very likely that we would get... And the reason I say that is that I did spend a lot of time tuning an implementation of Quick for this kind of scenarios, not exactly a scenario you mentioned, which is kind of the edge or the kind of tuning you do at the end of your, you tune for the main case first and then you go to the other cases. And that tuning involves things like checking the way you compute timers, checking the way you manage flow control windows, checking the way you do recovery. And so all that is work. And so basically the typical process that people get this simulation, they look at what's going on and say, haha, and they tune a constant here and there, and eventually they get to the level. But I think that's the great conclusion of your talk, is that if we do that work, there is no reason to believe that we will not get to the result.
Okay, I take from that a couple of points, and one of them being that maybe next IETF, people who are doing similar things with other scenarios or other quick implementations, let's get together. Let's spend some time actually drilling into that, not at the protocol level, but really at the results of what we're seeing to actually find out why and how.
Yeah.
Thank you.
Let's make Colin the end of this queue then, just so we can stay nearly on time.
Jana Iyengar. Wow, so many thoughts. First, I'm actually super impressed at how close Quick is to the PEP TCP and how far away it is from the VPN TCP, which also makes me super skeptical. Partly because, and to Christian's point, you're using Quickly, so I will say you're using the right implementation. I'm biased because I implemented the loss recovery, and so I'm at least partly responsible for some of the performance you're seeing, which is also why I'm trying to understand what the PEP is doing. So if the PEP is, so I don't fully understand the PEP itself that is being deployed. Is it a full terminator? Is it or is it just doing retransmissions?
Split TCP.
It's split TCP.
And
actually, no, that's obvious from the traces.
If you look at the traces, you'll see it.
Yeah, you're right. The straight vertical line is obviously a split TCP connection.
They receive traces, if you want to be clear.
So I think, thank you first for doing these experiments. This is awesome. In terms of I think at least part of what you're seeing is the difference between Reno and Cubic, because Quickly currently implements and deploys Reno.
Yes.
And this is a really large BDP link. And so there will be a difference there. And for the transfer sizes you have, I expect that Cubic is going to ramp up much faster.
We have looked at that, and I think that's partly it. And I think also there's some timer issues and minor details that could be fixed. So yeah, this is not a complete piece of work, it's a starter.
Yeah, and so two quick things. One, I'm super happy to continue working on this, and I'm happy to take this back and sort of fix the Quickly implementation for any bugs. But second, you might know that we have, Martin Zeman and I have been working on a simulator environment for testing these things. So it'd be good to actually validate this stuff with the simulator as well to see if we can replicate the same results there.
Excellent.
Thank you.
Ian Sweat, Google. Thanks for two things. One, for not using the Chromium Quick implementation, because so many papers and benchmarks have been based on it. And, there's always my personal concern that that's overfitting an implementation, and maybe we have some bug that turns out to be a performance enhancer. Number two, thank you for picking an implementation that, as close as I know, actually implements the most current version of the recovery and congestion control spec. And so this is sort of validating that what's in the spec largely works pretty well. And then the third comment is just, I think there are some approaches that probably could allow Quick to perform better here. Namely, and maybe TCP as well, BBR would be one of them. There's a lot of good evidence that PEPs are detrimental to BBR, not helpful. And so that might mitigate this, but I'm sure there are other things we could do as well. But thanks.
Okay.
Great work, Gori. Please keep it up. Do you know whether AQM is in use in the networks for any of this measurement?
They were not in these experiments.
They were not. Okay. So I'd be interested in seeing how that compared. And the other thing that I'd be interested in your future work looking at is comparison of fairness on the sort of the terrestrial network on the far side. How quick behaves compared to the sort of stock TCP.
Yeah, we probably will put an emulator in series with the actual satellite link to let us do some wireless effects and other things to concatenate two paths.
Yeah, maybe move the queue around to different sides of the link, that kind of thing.
Thank you.
Hi, Colin Perkins with No Hats. First of all, thank you. Great work. I kind of slightly like to echo the point Christian was making. I've seen a lot of, or heard a lot of people having read particular papers which talk about particular quick implementations, wildly over-extrapolate the results. And it's something that I don't know whether it's this group or the quick group might consider putting out a statement on how to benchmark quick and how to report the results and how to describe what you are benchmarking and what you're evaluating, because I think it is harming the perception of quick in that people are doing experiments with very early implementations of quick, comparing them to very highly optimized TCPs, and writing what look like very general conclusions when they're actually much more specific than they are.
Yeah, that's one of the reasons I wanted to stand up here, because we pull quickly and compile it and run the tests. So we want to keep it way up to date, and anything we do is patching that, because I think that's the only way to do it if you're benchmarking it now. Please don't use a G-Quick benchmark as your baseline. It's a different thing, but things have moved on. We really need to make sure we track the latest version in the quick working group.
And we really need to make sure that publications writing about quick are very specific about what they are testing and what are the implications of that.
Yes, I agree with that. Thank you.
Thanks so much, Gori.
Okay, next we have Ian from Google actually talking about the migration to IETF Quick, which is also quite exciting.
So I'm Ian Sweat. I'm here to talk about our migration towards IETF Quick from Google Quick. So where's Chrome now? V46, which is a Google Quick version that has no real meaning, but I'll explain to you approximately what it is now default enabled. We also enable V39 and 43 on the server at the moment. V46 is in variants draft 3 and below compatible. And it has transport draft 9 packet types, which I think actually are maybe still the same packet types that we have now. A future version will be in variants 4 compatible, which is the new, but that changes everything by like 1 byte, which is a relatively minor change technically, but I'm sure when we deploy that, a bunch of other things will break. V46 does have a quirk that actually only supports Google Quick style 8-byte connection IDs in one direction and 0 in the other. That was just a convenience because it allowed us to delay implementing all the variable length connection IDs, which took a ton of time. Thank you, David Skenazy. I don't know if you're here. So the rest of this talk is all about V43 to V46. So if you're wondering like what versions or what transition is he talking about, that's what I'm talking about. So the first thing is the change from public reset. So Google Quick has an unauthenticated public reset that's sent anytime you want to close a connection and you don't have any state or you're too lazy or whatever. But basically it's like a TCP reset. To connection close during the handshake and a stateless reset post handshake in IETF Quick. So why is this hard? It turns out in our code we have lots of spots we send a public reset, like well over 10, I think it turns out. And each one had to be fixed and tracked down, and it just took a while. Also, why does it matter? So handshake timeouts and idle timeouts are quite a bit longer than getting an immediate reset. In particular, idle timeout of our default is 30 seconds right now. It's extremely user visible. So, getting this wrong even like a few % of the time is a major source of user visible like problems. You really want to close the connection as quickly as possible in these sort of circumstances. When to send what? In gquick, if we have no state, we just send a public reset. That's pretty straightforward. IETF quick, if it's short header and no state, we send a stateless reset. If it's a long header and no state and it's initial, we try to start creating a connection. If it's a long header and no state and it's handshake, we send an initial close and hoping that they still have handshake or initial keys, which is sort of a, a hope, but it works in gquick at the moment. And if the version's not supported, we send VN. There are definitely some quirks here where you can get into this situation in the final version of IETF quick where you start receiving handshake packets and you're like, there is nothing I can guarantee to send in response that might close this connection quickly. And so you just have to send initial because it's the only thing you have a key for. Hopefully that will not turn out to be a practical issue. So let's talk about quick identification. It turns out at least one major company and increasingly more large companies are trying to do quick identification. Sometimes this is to just give you network monitoring tools like your network is this much HPS and this much, quick and this much DNS and this much all the other stuff. And sometimes it's also for selective traffic, enforcement. Basically, like I want to disable quick, or I want to disable quick if I can't get the SNI out, which we'll talk about later. So V46, when we started rolling it out, had a very large increase in post-handshake black holing. So it was about 2x V43. I'll explain it a little bit later how we determine post-handshake black holing. But again, this is one of those things that we track closely because it's very user visible. And waiting 30 seconds for your connection to time out before reissuing the request over a new connection is really, really painful. It also turns out historically these have been user focused. So a given user will experience this all the time. And the other 99.9% of the population will never, ever experience this. So it's not like every once in a while a web page is slow. It's like one user is having like a bad month or a bad year. So understandably, we don't like this. The confounding factor is sometimes the network just goes away, right? Like this happens. And so we have this base level of noise that we assume is the network going away, but we have no real proof. It's a very, you're never getting this to zero, right? Like, especially with mobile devices like Android and other things. And this is higher on Android for understandable reasons. All right. However, on April 13th, it suddenly fixed itself. Like, or basically fixed itself. I mean, there's a little bit of a gap there, but it went from 2x to like 1.1x over the course of a weekend. And we didn't change anything because we don't roll things out over a weekend. So what happened? Let's first talk about like what too many RTOs is, and then we can tell you what happened. On the fifth RTO in gquick, we found that that was a reasonable signal for closing the connection because it was black holed. As I noted at the bottom, 5 RTOs in our current implementation is kind of comparable to 7 RTOs in Linux, which I think is sometimes configured as a default. So, we're not so far off. We sort of stumbled upon this by accident because we were just having some unrelated issues, but it's enabled by default on Chrome Desktop. Definitely a heuristic. We could probably do better, but it turns out if you bump it up to 6, you're so close to the idle timeout, it doesn't really save you much. And if you make it any shorter, you do occasionally just kill a connection that you don't really mean to. So it's where we're at. Okay. But this is sort of our proxy for like black holing, and it's worked out to be a pretty good indicator. And in this case, it's a better indicator than we thought it was. So when we started debugging this, we're like, how can we get more data about when this is happening in a connection? And one of our team members had the great idea that we should add the number of number of packets that have been sent or received before closing the connection due to too many RTOs. And on the client side, the receive metric was very indicative. As you can see, all the extra black holing energy is all between 2, 3, and 4 packets. So basically, if you've gotten packet 5, like the rest of the connection is set, you are all good to go. And if you didn't get packet 5, then you're going to have a bad time and wait 30 seconds. Unfortunately, this typically happens after you've completed the handshake because 4 packets is more than enough to complete the handshake in Google Quick. So typically the difference between 2 and 3 and 4 is like, this is a case of you don't do 0 RTT, you get a packet, and then that's a reject, and then you do burn a round trip, and then it sends you to the cert, and that's somewhere between 1 and 3 packets, just as an explanation. So that's why sometimes 2, 3, or 4. But basically, this is like 2 flights of packets, and then like whatever it is block calling traffic. Great. Yeah, so it turned out to be quick mailbox identification. Suddenly improved when a vendor updated their identification software. So happily, most users of this software update or mailbox update weekly. We recently found out a few do not. Be aware of this because it's been fixed for a few months, but some particular individuals did not have it fixed in their local instance. So, if you're in the future, if you're debugging random quick issues and you're like, well, I think this was fixed by this vendor like months ago, beware that there is sometimes a long tail of updates. And it was impossible to diagnose because, of course, like we contacted the vendor and they're like, well, it's fixed. And we contacted the user and they're like, my life is terrible. And we appreciate both perspectives and I don't know. Okay, so let's talk about how to block quick if I was gonna ask you to block quick, because like this is sort of a favor and I'm not saying anyone's gonna change what they do, but it'd be really cool if you did. If you're gonna block it, can you ensure that all packets in one direction or the other are blocked? Like doesn't matter which direction, like don't care. You can let all the client packets go through and drop all the server packets. That's fine. Just try to drop all of them. Because anything else is really user visible, and Chrome now has some heuristics to try to avoid networks like this and avoid using quick on them. But it basically goes from consistent and utter failure to flaky hangouts or hangs and connection like loads, followed by like it works suddenly and you don't know why. So it goes just basically from failure to flaky. It's not fixing the problem. It's like a flaky test from a failing test.
In just about a minute.
Okay. Okay. So the other one I wanted to talk about from V43 to V46 is antivirus blocking. Suddenly we noticed that the usage of Quick on Windows dropped. We eventually actually traced it to a single company. At the time we found this out, V46 wasn't blocked. So we're like, hey, maybe they read the IETF invariance draft and decided not to drop the IETF invariant Quick, but decided to drop Google Quick. I mean, this is like me like thinking my most optimistic thought. This was not true. This was just completely false. We turned on V46 and 2 weeks later they like started blocking that. And the last thing is anytime you change the location of SNI, you're gonna break a bunch of stuff. There's a few more versions left, so we're gonna probably break some other things. And I'm really sorry, and it's a hard transition, but we're trying to do this as fast as we can. Okay. So I'll stop and give time for questions.
Is that your last slide?
Yes, that is my last slide.
Thank you, Ian, for bringing this here. This is something that I've been sort of sitting on the edge of my seat for a while to watch what happens when the gquick format changes. And as expected, it's already been ossified. This is exactly what we were afraid of, and this is exactly what we were worried about. And it seems like maybe some of them are actually doing updates, which is promising. But there's something that you mentioned. So the point that you were showing there, where the energy in too many RTOs is in the early few packets there. So that suggests a particular type of behavior in Middlebox, right, where they allow a few packets to go through and then die. And we've seen this before, and I wonder if this is actually, it's important enough now. I mean, we're seeing this again here, and I'm wondering if this is important enough that this is the sort of thing that you want to protect against. Meaning that if we keep thinking that all packets are going to go through or none of them are going to go through, it may not be compatible with the way that Middleboxes build their architecture, because I imagine that some of this is basically like, the forwarding thread sort of passing it on to a different thread that actually goes off to do detection of what type of packet this is. And by the time that completes and comes back, you already forwarded a few packets. I'm not sure exactly what's causing it to happen, but we've seen this. It may be worthwhile, two things. It may be worthwhile actually documenting some of this detection for others to also be able to use. I think it's super useful for non-Chromium clients to be able to build this sort of detection. The second, I wonder if this is something we can specifically detect as behavior and use for failovers in Chrome.
Yeah, we've thought about specifically detecting it, but it turns out that so far we've only observed one vendor actually doing this, and so we can email them and ask them to fix it usually. And so we've done that, and because the concern is otherwise we're ossifying the protocol on this weird thing where we have this workaround feature, and then we're stuck with it sort of forever, and so and everyone else has to build it too. So I mean, I guess I'd be okay if Chrome had to add it because, you know, we're early adopters and we're pushing things, but like if every quick client on earth had to add like a bunch of extra heuristics for the rest of time, that'd be kind of sad.
Thank you.
So you don't have any insights why this behavior of this vendor showed up?
Sorry? What?
Because you said it's one vendor, but you don't have any insights what the intention was there.
The intention in this case was they had an enterprise policy. They had both monitoring consoles and an enterprise policy. And the enterprise policy allowed you to drop quick. And the way they drop unknown protocols is that they give it a few packets in each direction. And then if after 2 or 3 packets, they haven't figured out what protocol it is, then they start dropping it. And so quick got classified in V46 as an unknown protocol and then got into this weird bin. So that's the other thing I was going to comment is this isn't good for like any transport associate like UDP protocol, like whether it's, you know, SCTP over DTLS, like all these things have the property that like if you complete the handshake and then black hole it, it's going to be like a really bad time. So for the general interest of transport innovation on UDP across the entire internet, I would like people to try to avoid doing this. Not
So
just for quick. I mean, this isn't just for us. This
Just
is
to answer
for
Maria's
anything.
question a little bit more, yeah, it's basically, it seems like, so what I've seen people talk about is that there are on the console of the middle box, it basically says packet received, cannot classify, and then it drops it. So it's possible that it's, you know, trying to do some classification on a separate thread and that thread eventually times out or gives up and then says, I'm done. And then it decides to black hole. But yeah, this is a huge issue. Unfortunately, the people who can change this aren't necessarily in this room, which is a frustration.
We cut the line and we would like people to hurry up a little bit. And if you're quick, you can still join the line, but please be quick.
All right. Thank you, Ian, for sharing this. I'll try to be quick here. First of all, a question. When we see the black holing, is it only on a per connection basis? It's not really like across the whole device to the IP?
Typically, it is actually across all the connections for that, like basically like every quick connection on that host starts getting black holed. Yeah.
Okay. Yeah, because
it's a middle box where all quick connections are going through. Yeah. So it's sort of a host-based based thing. Yeah.
Because you had mentioned the kind of like the background level, because we're always going to have some things that happen to drop off after 4 packets, but it's not really possible then to look at kind of all of the parallel connections, and you could see if this other connection dropped off and it was further along, maybe that's just a network impairment, but that would not work in this case.
Yeah. I mean, we don't really. I mean, our client's ID is not fine enough grain to actually even prove that fact, but yeah, I don't know. Yeah. Unfortunately, I don't think we can say for sure whether or not that's true, but yeah.
Hi, Brian Trammell. Quick question. I'll take the rest of this offline probably. As the co-editor of the quick manageability draft, I'm going to follow you a couple of issues to take this presentation into that draft. So you said that the dropping all of the packets for a connection is much better than dropping some of the packets for the connection from user visibility. And that's kind of obvious. And I think we should actually kind of write that down and yell it from the treetops in the IETF. And then you said that like, so for one of these, you get the first 3 packets and then you drop.
Yeah.
Are you seeing other things where you basically get like intermittent drops after you've actually like spun up data? Like, so data channels, like you get like, you get some actual data. It's like, oh, great. Now quick works. And then you drop every other packet. Or I mean, like, can you characterize a little bit more of the kind of drop patterns that you're seeing?
We do see some level of other like well post handshake dropouts.
Yeah.
Anecdotally, it seems to mostly be NAT related, where the NAT times out the NAT pour. And the fix for that is if you like, it typically happens in the following circumstance. It's more like the NAT times out. The server is sending a bunch of packets to the client. The client stops sending for some period of time, and the NAT timeout, instead of being a usage-based timeout, is a fixed timeout. So it's like, at 60 seconds, I'm going to time out this UDP like 5-tuple instead of after 60 seconds of idle, I will do this. And then you have to send a ping to reopen it.
I've anecdotally seen quite a bit of that on non-quick traffic as well. So there's something that you shot out in the treetops from another. Okay, cool.
It's not super common, but it does happen.
Yeah. All right. Thanks so much, Ian. Okay. So you guys asked a lot of great questions. We have 50 minutes of content to fit into 45 minutes right now. So we're going to ask Alexander, who had 20 to maybe 17 minutes or something like that, and similar for Roland afterwards. You cut a few minutes off so that people can ask you questions. But otherwise, up next is Alexander about packet loss signaling for encrypted protocols.
Thank you. I work for Orange, so we have, as an operator, we have the day-to-day issue of what to do to locate losses. It may seem a bit strange, but we are not completely aware of what happens in all nodes of our networks. That's a day-to-day truth. So maybe for many people, networks are just dumb pipes, but it's only true if someone can look at all the nodes. And if you get some OAM or something that tells you, okay, I got some drops on that interface, and you have absolutely no blind spots, it might work. But in the real world, it's not the case. So what we do is typically we do some dichotomy. We use some observer in the middle of the path and try to say if some problem occurs upstream or downstream from that point, and then reiterate. We do this on a day-to-day basis, and I've been done so for 30 years on TCP, obviously using sequence number and ACKs. That's trivial. But what do we do with encrypted transport like QUIC? That's much tougher, of course. So QUIC, as you may know, has something for RTT, measuring RTT with the spin bit, but nothing for loss for now. So we've got a proposal to solve that problem, which is based on only two loss bits, which we name Q and L. The Q, which is square signal, and L, which is the loss event signal. The square signal is just one toggle every n packets. So that's like the alternate packet marking, or also something mentioned by Kazuo a year ago about early loss detection discussions. So the qubit is just flipped every n packets. So when you look at it at a middle point, you just count the sequences and know how many packets have been lost upstream from the point. The loss event bit is fed by the stack itself and set to 1 whenever some earlier packet has been considered lost. So by counting both of them, you get the upstream loss and the end-to-end loss. So the end-to-end loss is just the fraction with L equals to 1, and the upstream loss is the difference between the expected number of Q and the observed number of Qs. And of course, the downstream loss is the difference, roughly the difference. So we've been running an experiment on Orange networks for real customers, with thousands of real customers in 4 countries with Akamai CDNs. So Akamai CDNs use a quick stack which is based on Chromium with proprietary patches, and in it we implemented the Q and L bits. As you might know, in the current quick specification, it's not possible to add those bits anywhere in the packet. So we did use some ugly level 3 trick. You poked those bits in the IP header in the TTL high order bits. This allowed, this is completely, okay, this is a hack, of course, not supposed to be generalized, but that's a way of doing a real life experiment today. With negotiation, with version negotiation in QUIC, it's absolutely not possible to do a large-scale experiment for anybody but people holding a browser or a popular application. We do not have any of them, so we were forced to do that. Okay, the topology of the experiment is the same for all 4 countries. You typically have an observer point, which is just below the Akamai CDNs, serving the access network. The suspect, the usual suspect in network troubleshooting are, of course, the internet path and the access network path. So whenever we start an investigation in our networks, even today with TCP, we'll always start at this point, because the key question to ask first is whether the responsibility is ours or not. The implementation details are as follows. So the quick stack patch by KMI just computes the QNL bits and insert them in the TTL high bits. And then we had to put a value for the period of the Q bit. So we chose 64 as a trade-off based on a few earlier experiments. And we will see that it's not so bad. So this gives, there are also another constraint which stem from the vehicle we used, which is the TTL high bits. Of course, since we use 2 high bits, it means that TTL must be below 63, but this was no real constraint as the Akamai server just set the value to 63. So what we do to gather data at the observation point is we do traffic capture with step aggregators. And we only capture the downlink path. We don't need the ACK flow. And also we truncate. The full payload is completely useless. So we only gather packet summaries with timestamps, IP ports, the QNL bits, and the payload size for debugging. The segmentation works by tuple and timeout, obviously, because we have no insight on the exact signaling going on in quick. And this allows to capture in one compact text file per flow all that happens, and then do various tests with the post-processing of the signals. So based on those files, you will see that both statistical and unit analysis can be performed. So here, before going into the analysis, I'll just plot a CDF of the flow size, because the flow size is important. As you know, the qubit just counts consecutive packets with the same value. Of course, if you got fewer than 64 packets in the flow, you see nothing. So what I've done here is plot the value of 640, which is 10 half periods of Q, which gives a boundary on the last chunk, the statistical importance of the last chunk, which obviously is incomplete. So if you just clip the data set above 640, you get roughly 10% in the worst case. But that's enough given the number of points captured. So the reviews we use to exploit the data are of 2 kinds. The first is statistical view, which we call QNL scatter plots. So we just give the bidimensional distribution of the loss derived from the Q and from the L bits. And then the unit view, if we want to debug what happened on that point, on this connection, we just plot an individual cumulative display of the losses, which is over the time in the connection, how many packets were lost, either end-to-end or upstream. So when we look at the first kind of plot, we analyze it this way. We've got upstream loss against end-to-end loss. The diagonal, of course, means pure upstream loss, because when the packet is lost upstream, it also appears in the end-to-end. The vertical is pure downstream loss. It appears only on the end-to-end measurement and not at all on the qubit. But the bottom right is supposed to be impossible, right? So we'll see. Then when we do unit analysis, you select one of these points and look at the way that the losses are spread over time in one given connection. In this example, you can see that both are completely synchronized, which means that it's pure upstream loss, which is every time there's a packet which is lost, it's also lost end-to-end. In this other case, you see only end-to-end, absolutely no upstream. So it's pure downstream. In this case, you see something which shouldn't happen, which is no end-to-end, and a completely insane and concentrated upstream loss, which in this case was based on missegmentation. The heuristics applied to the signal counting the qubits is supposed to do something about reordering, packet reordering, and in some cases it does poorly. And also missegmentation happens when the timeout is not enough to detect that some connection was reusing the same tuple. In this extreme case, you've completely uncorrelated losses, which happen to be due to observer path saturation, observer loss. Now we are going to look at the 4 countries. So these are the 4 scatter plots. Quickly, you can see that there's one of them which is an outlier, the bottom left. It's completely insane, and we'll see why. The first one, country 1, as you can see, is the main energy is on the vertical axis, which means pure downstream loss. There are a few points on the diagonal, which are really on the diagonal, which mean some events of upstream loss. And there is also some noise in the dragon area, which after unit analysis have been shown to be due to reordering. So again, that's due to when reordering happens, the boundaries of consecutive packets with Q equals 0 and 1 must be somehow accounted for. On country 2, it's much cleaner. The noise from reordering is very low. And we also see some energy on vertical axis and a few spots on the diagonal, meaning events of strong upstream loss. You can also see that they are not exactly on the diagonal, a bit below. And this has been accounted for by the fact that in Quick, you sometimes have packets going down, which are expandable. These are, for example, ACKs coming from window update. So we have correlated them to that. Country 3 is the insane one. And after correlation with other flows on the same capture path from TCP, it was shown that it was completely saturated capture chain. So the method also is able to detect something that TCP could allow, which is detected when your measurement apparatus doesn't work. Country 3 is cleaner too, and a few outliers due to missegmentation. Now you see the CDF, as a summary, a CDF, the downstream loss ratio, which gives you the difference between the X and Y axis and the earlier graphs. But plotting them as a CDF gives us a quantitative view that's better than the scatter plots. Okay, so to summarize what we've seen in the Dragon area, some noise is due to imperfection of the denoising heuristics, some is due to missegmentation, and some is due to observer loss, which obviously should not happen in real life. The summary is all these noise sources can be disambiguated by unit analysis, so we are not at all blind. And also the heuristics have been quickly developed and could be improved and reduce the noise. As a wrap-up, the unilateral deployment was made possible only because we didn't use the quick vehicle itself. So the TTL hack is key to that. And that's the only way to do a large-scale experiment. The signals were designed to restore TCP-like ability to debug networks, and they do. It works. And short of direct quick support, we do not expect to get anytime soon. Another vehicle is needed, so any suggestions are open. And the mechanism can be applied to any other protocol. It's not quick-centric. The only contribution that is expected from the stack is the L bit, which is the mechanism by which the stack tells that it has lost a packet. So the summary is that it works, and we really do need something like that to keep debugging networks. Short of that, with just the current state of Quick and no extensions, we are completely blind.
All right, we can squeeze in like 1 or 2 questions.
Ian Sweat, Google. Thanks for this data. This looks certainly interesting. One question I had is, for the spin bit, there's a fair amount of analysis of what happens if one or the 2 endpoints tries to, for lack of a better word, subvert the signal. It seems like it would be very easy for either endpoint to sort of convince a middle box of whatever signal it wanted, as well as some pretty crazy signals. Have you ever any thoughts about the ability to reject implementations that either are buggy or just aren't basically not complying with the scheme, or how to figure out when it's negotiated between a client and server and they are actively participating?
Remember that it's unilateral. So it's just a server side, right? So for the downstream pass, only the server sets the bit. And in the dominant usage, it's what we are interested in because it's where the congestion occurs in our networks.
Okay, so the most valuable signal is unilateral. Okay,
Yeah.
Modulo the fact that right now you'd drop half of these packets because the removing header protection would fail. Right.
Just to add to that, the alternative for TCP is also unencrypted and it's also subject to gaming, right? If somebody wants to send you interesting looking TCP stream, nothing stopping them.
All right, thanks so much, Alexander. So up next, we're going to have Roland talk about the RPKI Wayback Machine. And you've got 20 minutes for this, and then we've got one last presentation.
Okay, thanks, Dave. So I apologize to the people on the video in advance. I'm going to walk off the video to start an animation because my laptop didn't work with the presenter thing. Right, this is a talk about the RPKI Wayback Machine. My name is Roland Strijstek-Dij. I work for Nelnet Labs. I hope that somebody recognizes the slogan. Ziggy says there is a 50% chance we'll end up in 2011. Hands up, who knows Quantum Leap? There we go. Good. Right, so at Nelnet Labs, we make RPKI relying party software, which is called Routinator. And this has already seen quite a lot of uptake in production, with which we are very happy. But we also want to test our software ourselves and to see how robust it is. We found out that the RIPE NCC had a really, really nice data set that had all of the RPKI ROA data for all of the RIRs pretty much since the inception of RPKI. And so this is really cool data. So what we wanted to do was use that data to test Routinator. We wanted to run all of it through our validator software. We got dumps in tar gz files, and towards the end I'll tell you where you can find them because they're now open data. And we wrote a tool that we called Ziggy to transfer this back in RPKI time. So interlude, Al holding Ziggy and telling Sam where he's going to go next. Right, so what does Ziggy do? It is a Python script, again, open source. URL will be in one of the later slides. And you give it a date, and what it will do is it will try to figure out which of the RAR repository data it needs to unpack. It needs to recreate the towels, because the towels are missing in the tar gz files. And then it uses a tool called FakeTime to run the Routinator for the correct date. And we did this for data starting January 2011 until February 2019. At least those are the graphs that I'm going to show you. But actually, during this week, I did some more processing, and I have some really nice animations that I can show you that go until Monday this week. Right, for those of you who are less familiar with RPKI, a quick recap of some of the jargon that I'm going to be using throughout this presentation. The RPKI is the resource public key infrastructure. This allows you to set what are called route origin authorizations. And basically, this authorizes a certain AS to announce certain prefixes. This is cryptographically signed, so you can sort of validate that some AS was allowed to originate that prefix. And what we typically deal with after validation are called verified ROA payloads. Yes, that is an acronym in an acronym. And this is a cryptographically valid statement about a prefix from an ROA. Right. So first of all, if we look at RPKI, it started in 2011, but uptake sort of started slow. And then, as you can see, it is escalating towards today. It's really growing exponentially. What is also interesting is that the historic data that we got actually turned out to contain some flaws. You can see the little arrow on the graph that says first day RIPE data validates. Before that date, something was off in the manifest files that we got from RIPE NCC, and it didn't validate. And it is on our roadmap to use old RPKI software to also validate that data and see if we can make this graph cover the whole period. Another interesting thing that you can observe here is the spike in the green line from APNIC. And these were three ASs that suddenly deaggregate all of their ROAs, which basically means they disable their max length attribute, and rather than say, oh, this is a ROA that's valid for, say, a /16 prefix, and you can have sub-announcements of /24, they removed the max length and basically converted that into a whole bunch of /24 ROAs. And apparently this was a mistake in some software, and it got fixed pretty quickly. But the impact is quite visible. Of course, we also have to look at IPv6, because that's a modern protocol. Again, you can see more or less the same trend. It's far fewer prefixes for which there are ROAs, but the trending growth is pretty similar. It's still growing exponentially. It's going up towards today. And this is good news. So people are really starting to deploy this technology. So what I also looked at was the prefix size in VRPs over time. Because the hypothesis behind this was that as IPv4 exhaustion continues, you might expect to see VRPs for smaller prefixes. And actually, as you can see in this, this graph, that is true. So this is a CDF for 5 years. And in 2019, the fraction of prefixes that are 24 is sort of, let me say that. So that's going down. I'm trying to figure out what I wanted to say there. So and the same is true for max length, right? When max length is used, you can again see that the max length becomes smaller and smaller and smaller over time. So it's going down towards /24. For v6, we see pretty much the same thing. Again, the prefix size is decreasing over time, so we see VRPs for smaller prefixes. And this is also true for max length. There are, by the way, at the end of the presentation, there are many more graphs that I didn't have time to put in because I would be way over time if I presented all of these. But again, the takeaway from this is max length is decreasing for both v4 and v6. Right. Now, this one's a little bit interesting, right? Because there's been some debate about whether or not you should use max length or if you should prefer to deaggregate and have lots of ROAs that cover smaller prefixes. Because the reasoning behind this is if you have a max length, but you don't announce all of the sub-prefixes that are underneath that, you expose yourself to hijacking attempts. And what you can see is that max length use over time was going down until about a year ago, and it's slowly starting to rise again. And while we can't confirm this, we think this might be because people are now validating a lot more. And it turns out that people were announcing sub-prefixes that were not covered by the ROAs, and their announcements were getting rejected because of that. And then to fix that, if you're announcing sub-prefixes, it's easy to add a max length that is valid, and then your stuff will validate again. So it seems, I mean, this is kind of hand waving a bit, but it seems that this is a trend now. Again, so average prefix size. So there's a note there that says compare this to Jeff's story in routing. That was because I used this slide at the RIPE meeting in Reykjavik, where Jeff Houston presented something about the BGP table, where you also see a decreasing prefix size in the announcements that are in there. Well, no surprise, we see a decreasing average prefix size in the VRPs, both again max length and the prefix size that is in the ROA. Right. Again, for IPv6, we see pretty much the same thing, right? We see the average prefix size. So more ROAs for smaller prefixes. Now I'm going to go, so this is interesting. So this is something that I did over the week. I'm going to walk around so I can start, or is Miria going to start it for me? No. Okay, so I'm going to walk around and start that, sorry, on the video. So what we did here was we have a tool that will, is this the video? That one? No. Oh, okay. I need to click harder. There we go. What this shows you, this animation, is the coverage. So this is the, what we took was route views data for announcements that we see in BGP. We took the VRPs for certain dates, and we used the NRO stats to map those, the prefixes that we see in the announcements and in the ROAS to certain countries. And what this animation will show you is coverage. So this is the fraction of announcements that are covered by a ROA. And this animation runs until this Monday. And hopefully it's kind of visible on the screen. What you should be able to see in this is that it's slowly getting darker. And that means that we see more and more and more announcements that are actually covered by a ROA. And what you should also see is that we're now April, May, June, that this is accelerating towards the end. And I apologize that the screens kind of mangle the nice colors, but if you want the graphs, I can give them to you. Sorry? Can we play it again? Of course we can play it again. Oh, and yeah, you're from South America. They're doing really well in South America, as you can see. Right. Now, all of the tools that we use to create this are open source. So there's a slide at the end which shows you where you can grab them. Now, there is one more graph that I like to show you, and this one I like even more. What this shows you is accuracy. And accuracy we define as the fraction of covered announcements that are valid, right? So, and what we graph here are those countries that have an accuracy of 90% or over. So I cut off everything that has a lower accuracy because this will show you again that even there is already a high accuracy. So all of the countries that you see right now on April 1st, 2018 had an accuracy of over 90% for the announcements that are sort of, for the prefixes that are assigned to those specific countries. But what you will see is that the quality is really improving a lot. Again, what you see here is that, oops, some Canada disappeared, oops. But the takeaway from this is that quality is really, really getting good. So if you're not filtering based on RPKI, you really should be doing that because the quality of the data is very, very good, right? The accuracy is high. Can we go back to the slides? I have to stand here. Sorry, Miria is very strict. Right. So those were those two. Let me figure out if I can somehow, if people are interested, send me an email. I can get the videos for that. Right, to conclude, we wanted to test Routinator, and it turns out that RPKI took some time to standardize properly, right? Because we couldn't validate some of the older data. The data raises lots of questions, but it also shows you that you could deploy RPKI filtering in your network today because the quality of the data is actually very, very good. The next step that we want to do is to compare this against routing information in more detail, and we actually already did that. We submitted a paper to the ACM Measurement Conference. That was accepted, so we'll be presenting that in October in Amsterdam. And also, this is some free advertising as one of the general chairs of IMC. Please come to Amsterdam in October to the wonderful Internet Measurement Conference. With that, I would like to give a big thank you to the folks at the RIPE NCC for actually collecting and keeping this data, to Emil from RIPE to help us make this data available. This data is now available as open data. So if you are a researcher and you want to play with this RPKI data, go grab it off the RIPE FTP server. And also grab our free OSS tools, Routinator, the secure reading stats, which is what I use to do all of the computation for the maps that I showed,
And I turned the repository for Ziggy public earlier this week, so you can grab that. That will actually now download the data from the RIPE archive. So what you do is you run it, you give it a date, it will grab the right data, it will run Routinator if you have a local copy installed, and it will give you the VRPs for that date. And with that, I'm open to questions. Can I now go back to the mic?
Hi, Robert Kishtaki, RIPE NCC. One suggestion, I don't know about the exact incremental value that you would get out of this, but if there was an option to say disable manifest check, then you could fill in the gap that was before 2014 for the NCC. Yeah. The reason is the manifest is there to protect the integrity of the whole set, and if it's fair that it was not compromised, in that time period. Yes, there is a footnote there, but if you assume that it wasn't, then you would fill that gap.
Yes. Well, it's certainly something we want to do. It's just that with all the work we've been doing on the tool set, we haven't had time to sort of add the flag. But we're certainly going to do that. And we're probably also going to make all of the data that we validated, we'll probably put it up somewhere so that people can just grab the VRPs rather than having to run the validation themselves.
Hello, Brian Trammell, former RPKI skeptic. Thank you very, very much for putting all of this stuff together, so the entire stack. One of the problems that we've had in sort of trying to figure out what the state of deployment of a lot of these things are is that from the research standpoint, it's like, oh, you go and you read a paper from 2011, and then you read another paper from 2015, and you have 2 points, and it's very hard to draw a line. And here you have data points from every day, and the line is very apparent. One of the reasons I was an RPKI skeptic is sort of the base rate fallacy problem that you have when you're enabling optional security. There's a risk to turning validation on because the data is there's problems with the data. You might actually start rejecting routes, and you have availability risk, and you're trading off against security risk. The number so if I were trying to come up with a risk number from your data set, that would be 1 over accuracy, correct?
Yes.
Okay, because the things that are uncovered are not going to be a problem anyway. Okay, and the scale on the geographical data you were showing was like 90% to 99% of aggregated prefixes or of announcements. Announcements, and you're kind of hoping, yeah. And then the other.
Well, unique prefixes in announcements. Yeah.
Okay. Yeah. Perfect. Thanks. Okay. Thanks.
All right. Let's do this one last question, and we'll go to the last presentation.
Doug Montgomery, it's more of a comment on the last question, is that when you look at those accuracy numbers, you have to be careful to see if a route that's invalid might well be covered by another route that is valid or not found. We've looked at that, and the coverage is pretty high. The coverage that uses the same path is pretty high. Coverage that ends up in the same origin is pretty high.
Okay, thank you.
All right, thanks so much, Roland. So we had a late bit of juggling with the agenda, and we decided to have Jan come and talk to us about his recycling large-scale internet measurements for about 10 minutes. And so what we're going to do is bump the hackathon report that I would have done, but all is not lost. There's a link to the 3-minute hackathon talk that I gave. You can find it in the agenda. So in their updated slides for that. So take it away, Jan.
Thank you. So this is work we originally presented at PAM this year. Basically, this all started out, well, I've been doing internet measurements for the last couple of years. I was here at IETF in London and presented some stuff about Google Quick Deployment. So yes, this is a talk where also Quick is in. But we also scan for a lot more. We do DNS scans, TLS scans, HTTP2 scans. And the thing with these scans is we are looking for something very specific. But if you, for example, do a TCP IPv4 scan on port 80, 1% of all IPs will actually give you a SYNAX, so answer. What about the remaining 99%, right? So the idea basically that we had in this paper was, is there actually something we aren't scanning for, but we could have scanned for, or can we reuse the data that we already have? And to find that out, we basically captured all ICMP traffic that was ingressing our measurement networks. And as we do not generate ICMP traffic for ourselves,
this is either background traffic or traffic that is actually generated by our measurements. So the idea was, okay, let's study ICMP and let's study what actually is in there. And we were surprised because within a week we got, 637 million ICMP messages from a whole different number of IPs over 53,000 autonomous systems. And here you can see a plot basically where you can see that, yeah, well, they correspond to our measurements, which typically start at midnight if people correctly set their clocks. And yeah, let's not go into detail into this. And we basically, the first thing that we looked in was, okay, does it make a difference what we're actually scanning for? And yes, it does. So if we do like a TCP scan on port 80, you can see, yeah, we don't get a lot of destination unreachables or port unreachable messages, which is obvious because you would use probably reset for that, but there are still some of those. It also makes a difference whether or not we're simply doing IPv4 scans. We also do DNS-based scans where we have a lot of zone files. For example, the DNS-based scan, you can see that we get a lot of destination unreachable because host is prohibited messages if we do scans based on DNS data. And on the right, you can see a little table that summarizes basically what kind of messages we got, and I'm going to through some of those types and see what we actually found when we looked into those messages. I think it should start with redirect messages. So if you don't know what redirect messages are, they are basically used to signal a better path in your local network. So RFC 1812 actually states these three things, and the most important one is in the middle. It basically says, yeah, well, if the source address of the packet is on the same logical network as you, you may send these things. However, we never are, but we still got 80 million of those messages over the public internet. 100,000 of those are network redirects, which the RSA says you must not send because they don't actually make a lot of sense if you look at them. Well, but the majority are host redirects, and they affect roughly 2,000 ASs, and these are roughly 4,000. In these redirects, roughly were 400,000 destinations, and within all our DNS data that we actually have, we found also that 900 of them had an A record. And some of those actually redirect you to private address or reserved address spaces. Okay, this is not good. Next, we looked at source quench messages. So if you probably remember that, I didn't actually really knew what source quench was when I started this, and it's basically like ECN's grandparent. So the idea was when a router is congested, it send a source quench message to the senders. However, research found, well, it's kind of unfair if you do that, and it can lead to blind throughput reduction attacks. And you guys said, please don't send those in 1995. And you also said, please ignore those messages in 2012. And most OSs actually do that since 2005. Yet we still found that there are roughly 2,500 IPs located in over 350 ASs that still issue those messages. Mostly those messages were issued in the destination ASs, but we also found some that were issued on path. When we looked into some vendor manuals of some router manuals, and we found that most of those vendors also state that they removed it between 2000 and 2010, but you can still see it takes decades to get stuff out of the internet. So whatever you're standardizing, people will use it forever if they once activated it. All right. We also looked at another thing, fragmentation, and if something gets fragmented, because as I said, we also scan for quick, so our packets are roughly 1,300 bytes. And as it turns out, we use the ZMAP defaults in our scans, and they don't set the don't fragment bit. So we got some fragment time exceeded messages from another couple of scans where we do set those bits. We see that there's a bit of fragmentation. So another big bunch of messages that we actually got were TTL exceeded messages, which were kind of odd when I first saw them, because I was like, oh, well, are those internet paths actually so long? What are our TTL values? And it turns out it's the max in ZMAP, and otherwise we take the Linux default. So we ask ourselves, are the paths very long? Are there many middle boxes tweaking our TTLs? Or are there maybe routing loops? And we basically performed a whole bunch of trace routes to see if there are loops. And we were able basically to find roughly 440,000 /24s from roughly 20,000 S's that were unreachable due to a loop. Interestingly, we could find 130,000 or the pass where we had all IPs of all involved routers. And with simple checks, we could see that roughly 5,000 of those actually also cross AS boundaries of these loops. However, you can definitely make that better. Then we also looked at whether or not these loops are persistent. So we compared basically trace routes from 2 weeks apart, and we found that loops from roughly 150 ASs disappeared, but there were still 404 subnets unreachable, 1,000. We also found loops in our upstream ISP in the German research network, which was nice because we can contact them and they confirm the loops, which they didn't really like. They fixed the loops, and for a specific loop, they could tell us basically it was a static route they had once in one router, then they removed it in another one, but it was basically still forwarding packets to the other router. But this router had no knowledge about that route anymore and sent it to its default route, which was the first router. And yeah, so it started to loop. All right, this brings me to my end. So as you probably know, the internet is full of deprecation and badly configured systems. We have got more odd things in our paper. The nice thing, I mean, we all know that, but the nice thing is we could find that without actually doing any new measurements. These were all done from, apart from the trace routes, were all done using data that we already have but never looked at. Lots of routing loops. Our data set is partly available until last month, where obviously our drives ran full. Thank you.
All right, we got 4 minutes left in the session. And questions for Jan, or if we don't have those, any other comments on work for the group would be great. Along the lines of, for the last 3 times we've participated in the hackathon, so you're welcome to talk about that. Anything? Thanks, Jan. Okay, so along the lines of the invitation to talk about topics for the group, Miri and I have been encouraging people to do measurement work here, not just report it. So we've been doing that in the hackathon, and the large scale scope of it is, what I've been trying to do in the hackathon is create anonymity sets for World Wide Web clients. And there was some really nice work at the ANRW. If you haven't seen the program there, check that out, about what can you learn from an IP, where they surveyed the server side IP addresses and what you can learn from those. And in PRG, and I'm also interested in doing this, creating anonymity sets somehow of the service side so people can't profile encrypted traffic and determine what you're talking to. So if that's something you're interested in, get in touch with me, or we can talk about it on a list, or you might be able to do it in Singapore at the hackathon if you'd like. That's all we have. Thanks so much. That was great. I didn't know.